In this lesson, we'll investigate graphs of tangent, cotangent, secant, and cosecant functions. Let's recall how did we come up with values for special angles for the function of tangent or cotangent. Tangent of any angle t was the ratio of y over x. And if we have the unit circle with the coordinates of points defining special angles, then for example, tangent of pi quarter, if the terminal is going here, is y over x. So this is x, this is y. Since both coordinates are the same, then the ratio is really 1. So tangent of pi quarter is equal to 1. And this is a very special point on a graph of tangent function. So it's a good idea to remember this. Aside of this, we have tangent of pi thirds is root 3. Tangent of pi 6 is root 3 over 3. Tangent of 0 is 0, so that's also good to remember. And some other values. So we can collect lots of values and just plot it in a system of coordinates to find out what's the graph of tangent. And we'll do it in a second on an applet. Similarly, cotangent. Cotangent of an angle t is defined as x over y. So the value of cotangent for the angle pi quarter is exactly the same as for tangent. It is the ratio of the same numbers, so it's equal to 1. So this is the same value. However, for some other angles, let's say for pi 6, that will be the first coordinate divided by the second, which is root 3. So here we have root 3. And we can build this table by using different inputs for cotangent and find out the value. Again, we can plot it in a system of coordinates and obtain a graph for cotangent function. Notice that for the function of cotangent, if we think about input 0, then according to definition, we'll have to divide 1 by 0. So cotangent at 0 doesn't exist. Similarly, tangent for pi half. See, pi half passes through the point 0, 1. And since tangent is defined as y over x, well, we can't divide by 0. So this point can't be taken for the domain. Well, let's look at our applets that will put together the values for tangent, cotangent, and create graphs. And then we'll investigate those graphs. Here we see the graph of 20 times tangent, so you may want to consider 20 as one unit. Observe the value of tangent is the same as the height of the segment connecting point 1, 0 with the terminal of the angle. And now cotangent curve, again assume this number around 20 represents one unit. Okay, so we saw the two graphs. Let's recall them. For tangent, we have the following situation. If we want to graph just one full section of tangent, it will have two asymptotes at negative pi half and at pi half. And the graph looks somehow like this. Goes through 0 and is trying to approach those asymptotes. So that's just one branch, and this branch repeats itself. The important points to remember are the center 0, the asymptotes at negative pi half and pi half, but also this point pi quarter 1 and negative pi quarter negative 1. So those are quite important points to watch because they keep the shape. We'll always try to plot these three important points and the asymptotes and then try smoothly connect towards asymptotes. As a matter of cotangent, the shape looks very similarly to tangent. However, the asymptotes are at 0 and at pi. So this branch is shifted, and also the graph goes the other way around, is decreasing rather than increasing. So the three important points are the center is at pi half, and then at pi quarter we have 1, and at 3 pi quarters we have negative 1, somewhere here. we connect these 3 points. So the graph looks somehow like this. And obviously this branch repeats itself. So that was tangent, and that's cotangent. So keep those curves in mind because we need to know them off heart. And now let's investigate properties of each of these functions. So basic properties of the function of tangent, which we see the graph here. Let's look at the domain. It's not like with sine and cosine. The domain is not all real numbers because the points where we can expect asymptotes will have to be excluded. And look at those points. Those are like pi half and then they jump by pi. So the repetition of this pattern is every pi. Okay, so the domain is all real numbers x such that x is different than the points that I marked here. That means it's different than pi half plus any multiple of pi, where the k is an integer to indicate a multiple. Okay, so that's the domain. The basic shape of tangent consists of just this branch, the closest to 0. And then this shape repeats itself every pi. The range, as you see, the range can be all real numbers, in opposed to sine and cosine that had the range only from -1 to 1. Now we have all real numbers. Period, as I mentioned, the situation repeats itself every pi, so period is just pi, not 2 pi. Symmetry. Well, if you look at the shape, it is symmetrical in the origin. So the function is odd, which means that tangent of -x is the same as negative tangent of x. Y-intercept, well, there is one y-intercept 0, 0. X-intercepts, there's a lot of them. So you see the x-intercepts are 0, pi, negative pi, and so on and so forth. So every single pi starting from 0. So we can record it's all real numbers of the type k times pi, where k is an integer. And vertical asymptotes, now we need to generate equations of those asymptotes, and any equation will be of the type x equals to pi half plus k pi. So those are exactly the points that were excluded from the domain for k being an integer. We can also notice that each branch of this tangent function is actually increasing, but it's increasing only within this full period, basic period, not the whole function. And here we have cotangent. It's decreasing in the first period. The domain of cotangent is the set of all real numbers such that our numbers are not equal to 0, pi, 2 pi, and so on. So they are different than k times pi, where k is an integer. The range is the same as in tangent, that means all real numbers. Period is the same as for tangent, which is just pi. Symmetry. Again, we have the same situation as for tangent. Any point can be transported to the other side of the center with the same distance and hit the graph again, which means that we have symmetry in the origin. So the function is odd. So we have the same property. Cotangent of -x equals negative cotangent of x. Y-intercept, oh, this time there is none. No y-intercept. X-intercepts, the x-intercepts are those points that come through pi half and then adding any multiple of pi. So x-intercepts are all real numbers of the type pi half plus any multiple of pi for k being an integer. Vertical asymptotes, they come through the points that were rejected from the domain. So the equations of vertical asymptotes are of the type x equals k times pi for k being an integer. Okay, so we know quite a bit about tangent and cotangent. Maybe one more property. Both tangents and cotangents exactly half away from the center towards the asymptote at pi quarter, they have a value 1, and negative pi quarter, negative 1. So those points are on the graph. And for cotangent, again, pi quarter, and we see the value is 1, negative pi quarter, and we see that the value is negative 1. So those points are kept. Also here at this point it will be negative 1. And now we will talk about properties of secant and cosecant, but first let's look at the applet to see the shape of these two functions. The graphs of secant and cosecant are done with the factor of 30, so consider 30 as one unit here. As you see, the bottom or the top of the graph is exactly at 30 or negative 30. Okay, we saw the shapes. Here's the secant function, which, as you remember, it's reciprocal of cosine. So if we have this gray line, which is cosine x, and we take each value of cosine and take reciprocal of it, we create a graph of secant. So reciprocal of 1 is still 1, and we can't take reciprocal of 0. That's why we end up with asymptote at the points where originally cosine was 0. Okay, so looking at the graph of secant, let's state the domain. Well, it's not all real numbers because we have to exclude the points where normally cosine was 0. So it's all real numbers except for those of the type pi half plus k pi, where k is an integer. So pi half, and then we can jump every pi. Range. When I look at projection of this graph onto the y-axis, not all values are covered. Everything from negative infinity up to negative 1, but then those points between negative 1 and 1, they are not covered at all. We don't have values like that for secant. And the values start again from 1 to infinity. So the range is from negative infinity up to negative 1, including union from 1 to infinity. Period. Well, the situation repeats itself every 2 pi. The curve looks the same, but once it's in the top and second time is in the bottom. So we must wait 2 pi before the whole pattern repeats itself. Therefore, period is 2 pi, the same as for cosine. Symmetry. If we look at y-axis, the shape is like a book. So we have symmetry in y-axis, which means that the function is even. And that's not a surprise because cosine was even, so this reciprocal will be even as well. That tells us that secant of negative x is the same as secant of x. Y-intercept, oh, there is 1 at 0, 1. X-intercepts, none. There is no x-intercepts. Vertical asymptotes, they happen at those points that are out of the domain. So any line with the equation x equals pi half plus k pi is a vertical asymptote for k being an integer. And finally, the graph of cosecant, it's a reciprocal of sine. So if we graph sine first and then take every value of sine and take reciprocal and plot it, we obtain cosecant. So this branch is positive, that branch is negative, and we have asymptotes where originally sine was 0. So domain. all real numbers except for the points of the type 0, pi, 2 pi, and so on. So k pi, where k is an integer. Range. Similarly as for secant, the range is from negative infinity up to negative 1, and then there is a jump from 1 to infinity. So range, negative infinity, negative 1, union, 1 to infinity. Period. Similarly as cosine, the situation repeats itself after 2 pi. Symmetry. Oh, this time the point goes across the center to the other side at the same distance. So that's a central symmetry, which means that the function is odd. And that tells us that cosecant of negative x equals negative cosecant of x. Y-intercept, oh, there isn't any, so none. X-intercepts, also none. Vertical asymptotes are the lines that are coming through the points that were out of the domain. So the equations of such asymptotes are x equals k times pi, where k is an integer. So now when we know already the basic shapes of tangent, cotangent, secant, and cosecant, let's try to graph functions like 1/2 tangent, negative cotangent, 2 cosecant by using basic graph transformations. To graph the first one, since we are multiplying the function of tangent by 1/2, then the regular tangent, the basic shape that had asymptotes at negative pi half and pi half, so on this piece of graph we can fit actually 2 periods. This basic graph will be dilated by the factor of 1/2 in vertical axis, which means that our 0, 0 will be at the same place, but the angle pi quarter will result not in 1, but in 1/2. So it will be a little bit flatter, and for negative pi quarter, the value will be negative 1/2, so somewhere there. And now let's volunteer a shape. The shape starts from the bottom, goes towards the top, trying to follow the asymptotes, but it must go through these 3 points. So it goes somehow like this. And another branch, so here, here, and there, and try to make a shape. Somehow like this. Okay, as you notice, this function f of x doesn't differ too much from the basic tangent. The basic tangent looked actually like that. A little bit steeper. And this is a little bit flatter, but the shape is very similar. Okay, let's look at g of x. That's negative cotangent. So let's recall the asymptotes for cotangent. It was at 0 and at pi, so that's a basic period. And cotangent normally goes like this. So that's a basic shape. And what we need to do to it is just change the sign. That means we need to apply symmetry in x-axis. In the first case, we apply dilation in y by the factor of 1/2. And now symmetry in x-axis. So this point becomes here. That's the same. And this one is over there. And we graph the shape. Somehow like this. And the last function, h of x, on this graph. Let's recall the basic function of cosecant, which is the same as 1 over sine. So sine looked somehow like that. Oh, we have a little bit short of graph here, but that's okay. This point will be 2 pi. Therefore, regular cosecant, it looked somehow like this. 2 branches. And those are the asymptotes. But now we have to graph 2 times cosecant, meaning that we are using dilation in y-axis by the factor of 2. So this point 1 becomes 2. the asymptotes will be exactly at the same places, 0 and pi and 2 pi, but the shape itself will be a little bit farther apart from the center, from the x-axis. That's the only change. It still follows those asymptotes. So the red shape is the shape of h of x. Similarly here, this part will go somehow like this. So the previous exercise was to apply stretching or shrinking vertically. And now how do we deal with stretching or shrinking horizontally? If we want to graph functions like tangent or cotangent of b times x, where b is any real number except for 0, then it's a good idea to know the period of the new function, how the period changes. Well, the period changes according to a similar rule as for sine and cosine, except that the new period is the basic period of the basic shapes, tangent and cotangent, which is pi in this case, over the absolute value of this constant b. So for sine and cosine, we took 2 pi. The same will be for secant and cosecant, will be 2 pi over b. Only for tangent and cotangent is pi over b. Okay, let's practice graphing such functions. So it's a combination of changing the period and dilating in y-axis. Well, first let's graph tangent of 1/2 x in blue. What do we do with the basic function of tangent x to obtain tangent of 1/2 x? Well, we apply dilation in x-axis by the reciprocal of this coefficient, that means by 2. Okay, therefore the period should be twice as long. Let's see if this rule will show us the same. Well, period is pi divided by 1/2, which, yes, it is 2 pi rather than pi. Okay, so to graph tangent of 1/2 x, the first thing would be to graph asymptotes closest to 0. So, since the full period is 2 pi, and the shape goes half away from 0 to the right and half to the left, then it must be pi to the right and pi to the left. That's why we have full period 2 pi from here to there. So this main curve of tangent will have to fit within these two boundaries. Okay, and it comes through 0, 0, and halfway between the center and the asymptote we have a value 1, and the other way -1. We can volunteer a shape somehow like this. And to get the final function f of x, we need to dilate vertically by the factor of 1/2. So dilate the blue shape in y-axis by the factor of 1/2, which means instead of 1, we'll have actually value 1/2 and -1/2, and 0, 0, asymptotes the same, so the shape is a little bit flatter around 0, and then goes towards infinity. The second shape, now we have cotangent of pi x, so the new period is pi divided by pi, which is 1. And cotangent starts from the y-axis, and the first branch opens up to the full period, that means up to the 1, so the asymptote will be here and there. And cotangent is decreasing, that will be the center of this branch. Normally halfway it would be 1, so this yellow graph will be the graph of just cotangent of pi x. It will look somehow like this, pretty steep. And now to graph actually g of x in green, 1/4 of cotangent of pi x, meaning that every important point I need to multiply by 1/4. So instead of 1, I will have 1/4, and the same here. So it's the same shape but flatter around the center here. So that will be the g of x, the green one. Obviously we can graph another branch. It will go like that. Okay, so we know how to use the basic shapes to graph the new functions involving tangent or cotangent. In the next exercise, we're asked to find the formula for the given graph. So now we have the graph, we need to recognize the shape and adjust it so it will have the shown properties. Okay, this function is decreasing, so someone could say that's something to do with cotangent. And yes, we could use cotangent, but we could also use negative tangent. And why I would suggest negative tangent? Just because the asymptotes are positioned symmetrically about the y-axis, so it's probably easier to build a formula around tangent than cotangent. Cotangent will have to be shifted, and tangent is as it is, with no shifts. And now, looking at the period, which is from -1 to 1, so it's actually 2, we need to recover the number b, the coefficient b by the x. So b is pi divided by the period 2, so pi half. Okay, therefore our function must have a formula tangent of pi half x as an input, and it must have a minus in front of it somehow, because the shape is decreasing rather than increasing, which is a feature of tangent. One more thing, this works somehow like an amplitude, but it's not an amplitude. It's just the important point, which normally was at the halfway here. This point's supposed to be -1, but it is -1/4, which means that I need to multiply the tangent by 1/4. So here it is the formula. That's our f of x, which is graphed here. And you're welcome to plug it into the calculator and see if the shape is like that. Obviously, observe the scale as well. The second graph, what this can be? If this is 3, then this one is 1, therefore here we have 1/2. Okay, so this tells me that kind of amplitude, it's not an amplitude, but it's related to it, is 1/2, because normally the shape will start with 1. But it starts from 1/2. Is it secant or cosecant? Well, the basic shape would start from 0, 1, which leads me to believe that it's built on cosine. So reciprocal of cosine is secant. Therefore, this shape must be connected with secant. Now, the full period. Well, if this is 1, 2, 3, well, there's 4 units. The full period is 4. So since period is 4, the b number is the regular period, which is 2 pi over 4. So it's pi half. Therefore, we have 1/2 secant of pi half x. Let's call it g of x, g function. The next two graphs are combinations of trigonometric functions, absolute value, or a product with some other polynomial functions. For example, here we have sine x multiplied by x. Well, you can use graphing calculator and see the shape, but try to analyze try to get some insight how come the shape it is as it is. Basically, whatever we have before the sine, that stands for an amplitude, but this amplitude is changing along the x. Well, the y equals x, that's this line. Since amplitude is actually absolute value, so we should consider the y equals -x as well, because if this will be negative number, the amplitude will still be the same. Therefore, our shape must be enclosed between these two lines. And the shape is of sine, so normally sine waves like this with the amplitude 1. But now the amplitude changes. So if normally we had 0 at pi, our graph will still have 0 at pi because 0 times anything is still 0. So all the zeros will be kept at the same places. That's pi, 2 pi, 3 pi, and so on. And 0 and -pi and -2 pi, and so on to the left. So zeros are kept at the same places. However, the amplitude changes. So normally we had value 1 at pi half, but now will be 1 times pi half. So at pi half, we have value exactly pi half. That's why it's exactly on this line y equals x. The same here, this point will be on that line. The value for this point at the middle will be on this line y equals -1/2. And then we try to connect those bumps like that. So that's for positive x's. Now notice that this function is actually even, because if we plug it in -x for x, then we have -x here, but sign is off. So if we pull this minus outside of the sign, then two negatives makes it positive. So we end up with the same f of x, which means that f is even. That's why the graph to the left is a reflection of the graph to the right. So it's a funny wave like that, with higher and higher amplitude, oscillating between these two diagonals. Well, let's look at tangent absolute value of x. If we draw the standard tangent, the basic tangent function, it will go like this. Somehow. And another branch. So that was somewhere here. And this branch. Now let's do g of x in purple. If we apply absolute value around the input x, then recall from transformations of graphs that if x was positive, the absolute value doesn't change anything. So this graph will be exactly the same to the right of the y-axis. But whatever it was on the left-hand side, it will be forgotten, and the right-hand side will be flipped over the y-axis to the left. So this point here will be kept, and this shape will go like that over here. So that's tangent of absolute value of x. And the last two interesting graphs. The first one shouldn't be too difficult to graph. You just start with secant x, which has asymptotes at pi half and 3 pi half. And the graph looks somehow like this. It goes through these points and is trying to follow the asymptotes. Now the h of x, which is absolute value of secant, h of x, will be in red. If we had a branch that was negative, it will be just flipped to the top to make it positive. That's the only change. Everything else will be the same. So this branch is the same, and that one is the same. So the red graph is our h of x. It could be a little bit more trouble with this interesting case, x squared times cosine x. Well, first of all, is this function even or odd? Let's see. P of negative x squared cos negative x. We know that cosine is even, so that's the same as just x squared and just cosine x, so it's the same as p of x, which really means that p is even. Okay, that's nice to consider. We also have similar situation as before. We have an amplitude that follows the shape of x squared. So if I graph x squared, starts with 0, 1 is somewhere here, so 1 will be somewhere there. Okay, and 2, maybe here, it should be already 4. So approximately follows that shape. Okay, I'll have to draw the same shape reflected approximately here to the bottom, because our curve is going to oscillate between these two, x squared and negative x squared. So cosine normally starts from 1, but remember it is multiplied by 0 at 1. So it will have to start with 0. then it will always stay below this line. It will never go above. And we'll have to reach the next 0 at pi half, because then cosine is 0, even though x squared is not. So the shape will follow somehow like this. And then at pi, we'll have a value -1. But this will be multiplied by pi squared. So it's negative pi squared. So it's pretty steep down. So it's hard for me to find this point. It's pretty down. But then it will turn back because, remember, at 3 pi half, somewhere there, the graph needs to hit the 0 again. So that bump needs to go back pretty quickly and then go even faster up and down and up and down. So similarly to the other side, since this is even, so it's easier for us to graph, it will go somehow like this. Pretty steep down, somewhere there, and then go back towards -3 pi half. So it needs to go back and then go up and down and up and down, this kind of shape. So your calculator will be a lot better to see the shape, but it's an interesting case. So I hope you will enjoy investigating the shape with your calculator.